Okay, so we'll get back onto the lectures then, and we will. So last week I think we did Deutsch's algorithm. So this is another type of quantum algorithm, and it's kind of quite an exciting sort of topic of quantum teleportation. But basically it's actually also just a type of quantum algorithm. It's fairly simple quantum algorithm, as you'll see, but the interesting thing about this is not so much that it does something, that you want to compute or anything, but actually the interesting thing is that basically you have this effect where state becomes teleported sort of between two places, and so it's a lot like what you see in sort of Star Trek, but it's not exactly like that, as we'll see. Okay, so the page turner working first. Okay. Right. So what is teleportation, or what is quantum teleportation? So basically the aim of this is to send an unknown quantum state from Alice to Bob. So Alice over here has some quantum state, and for what we're going to do, it's going to always be qubits. So Alice has a qubit here, it's got some quantum state on it, and the aim is to send that to Bob, right? So Bob has some other state, and the idea is that Bob at the end gets this state. And one of the interesting things about this is that actually Alice nor Bob actually ever know what the state is, or at least they don't have to know what the state is. So they can do this procedure, and Alice has a qubit, and she may never know what it was. She knows she's got something, but eventually it gets sent to Bob, and even Bob may not know what it is exactly, and at the end of the procedure everybody knows that, well, whatever Alice had got sent to Bob, and that sort of completes the protocol. So so the final stage is like this. So let's talk a little bit about what quantum teleportation is and isn't. So what it sort of isn't is this kind of image that you have from Star Trek, where the person walks into the teleporter, and then they go all fuzzy, and then they get teleported to a different planet or something like that, right? So when you have it like this, then what it kind of looks like is that the atoms in this person's body sort of somehow disappears, right? And then all these atoms kind of turn up somewhere else. So it's not quite that, actually. So quantum teleportation is not really that, because of course this qubit here, which is probably some kind of physical object like an atom, the atom can't just disintegrate and just go somewhere, right? So the atom or qubit that the Alice holds is always there from beginning to end, and also the qubit that Bob holds is also there from beginning to end. So those are there, and it's not like the atom is somehow moving or something like that. But what does happen is that the quantum state of this atom does go from Alice to Bob. And so even though this is not quite the Star Trek thing, there is an element of sort of truth to why this is sort of reasonable to still call teleportation, in the sense that, well, the quantum state is sort of the ultimate reality of the state. So you might sort of say that, well, what is anything but just a quantum wave function? So you and I, we're all basically just some kind of very complicated quantum wave function, and if you had all that information, that basically is you. You know, that is your state. And so, in the sense that if you take the point of view that the state of something is really the quantum state, and that's like the ultimate description of what something is, in that sense, well, that state is being transferred from Alice to Bob. So you know, you can just almost think of the atom as just some, you know, mediator of the transition. A bit like, you know, if you're watching a, you know, YouTube video or something like that, you know, the reality of the video is not like the television, right? The television is just like the display or the computer or your phone, you know. The reality of the video is like, you know, is in that digital information of that video, right? It's not because the TV's there, because you can do it on any TV. A bit like, if you think of it like that, the state is the real identity of the thing that you're transporting. Then these atoms are a bit like the TV or your computer or your laptop or your phone, and the reality is, you know, the actual state, and that's the thing that we're transmitting. So, you know, okay, so it's not exactly like, you know, what was on Star Trek, but in a way it's still a little bit, you know, you can sort of, if you change your point of view, you can still think of it as teleportation. Another aspect is that we learned from the no cloning theorem that it's actually impossible to make like a second copy of your state psi, right? So remember from the no cloning theorem, we were saying that, okay, if you have some state psi, and let's say you had another qubit that was sort of a blank qubit, just set it to 0, there's no circuit that does this, right? So you have psi, and then out comes 2 copies of psi. So, you know, this circuit is impossible. So, in that sense, you know, it's impossible to just make a copy and send it somewhere, right? What's interesting about the teleportation is that even though this is impossible, doing something like, you know, and this is what we're going to see, is basically doing something like, okay, so I'm not going to say what the state is, but having a state here, and then you do some operation, and then the state coming out somewhere else, this is actually possible. So that's so it's actually still consistent with no cloning theorem, and also it sort of means that the state on one side has to get destroyed in order to come out the other side. So in that sense, it's also a bit similar to teleportation. It's not, you know, because there's no copying device. If we stepped into the teleporter and then, you know, somewhere on a different planet there's another you, you know, that's not really teleportation, because what's supposed to happen is that you're supposed to disappear here and you're supposed to reappear here, and that's exactly what happens. Okay, so so I said right at the beginning that Alice and Bob doesn't need to know what the state is. So, you know, why did I emphasize that? Why is that such an important point? So, if Alice knew what the state was, so say she knew it was this thing, you know, say Alice knew alpha was I over 2 and beta was root 3 over 2, just a random example, of course. So if she knew what it was, then this would not be so amazing in a way, because all she needs to do is just phone up Bob and say, hi Bob, this is my state, can you make it over here? And then Bob shoots a few lasers and stuff, makes that state. So if it was that, then of course this, you know, okay, obviously you can sort of do that. So there's nothing so amazing about that. So Yeah. So basically, you know, not knowing the state is kind of an important part of this because if you knew it, then you could just go and prepare it. So the fact that you can kind of do it without knowing it is the interesting thing. So, okay, fine. Alice may not know what the state is at the beginning, but why doesn't just Alice go and, you know, just measure the state, okay, go and measure it, figure out what the state is, and then tell Bob what the state is, right? That seems like a reasonable thing to do, you know, particularly classically, because, you know, you can always figure out what the state is, right? But as we've kind of already learnt, in quantum mechanics, if you don't know like a particular state, and you try and measure it, you can never really figure out what it really was, because, you know, you've got this state, alpha, beta, whatever it is, and then you go measure it, say in the Z01 basis, and then say it gives 1, right? That doesn't really tell you that it was really in 1. It's a random process, so, you know, it could have been 1, but it could have also been just, say, alpha and beta were 1 over root 2, then it just happened to get 1, 50-50, or actually all it really says for sure is that beta was not 0. You know, the fact that you got 1 means it's not 0, but apart from that, it could have really been anything, actually. So, you know, in this case, if Alice goes and measures and then phones up Bob, but, you know, this is clearly not really a very exact kind of protocol because, you know, Alice will obviously know that it's kind of a, could be random result, and then so this is sort of the best they can kind of do using the measurements, right? So Bob would go, okay, well, you know, who knows, but let's prepare 1 and hope for the best. So there's a kind of a theoretical limit to actually knowing how well you can estimate a quantum state if you didn't know what it was. And I'm not going to go into the details of that, but in this paper here in 1995, these guys work out that if you have like n copies of the same state, so you've got a bunch of qubits and they're all in the same state, okay? So actually, if you got like more copies of it, it gives you slightly better chance of working out what it is, because you can do all kinds of measurements and try and work out what the state is, right? So you do like a 0-1 measurement, basis measurement, and plus minus basis measurement, do various measurements, and kind of work out probably what it is, right? So these guys have the result that this is the fidelity. I forget if I told you guys what fidelity is, but basically fidelity is basically a measure of how good or how close some two states are. So basically 1 means that it's like 100% accurate. This is a number that goes between 0 and 1. And fidelity of 0 means that it's like exactly orthogonal, right? So if the state was 1 and then you were guessing 0, your fidelity would be 0 because these are orthogonal states. So these guys give a formula that if you've got n copies of the state and then you can just do whatever measurements that you like, then the best fidelity on average that you can get is formula n plus 1 over n over 2. So for 1 qubit, that means that the best fidelity is 0.666. So basically what that means is that if you've got an unknown state and you've only got 1 qubit, then you will, you know, be able to only get within 66% of what the actual state is. So, so basically, with 1 qubit, this is not going to be very accurate. If you got more copies of the qubit, it could be more accurate. Obviously, as n goes up, this approaches 1, right? And so the more copies you have, the better idea you have of that. And so if you had like an infinite number of qubits, then yeah, they could do this. Alice could just phone up Bob and just say, okay, so I did an infinite number of measurements. Took a long time, but I worked out that it's this state. Bob, please go and prepare that. And then so that would work, but of course it requires an infinite number of qubits. Okay, so the best you can basically do with 1 qubit is 66%. Okay, so basically just remember that. So what I'm going to show you is a way of getting not 66%, but basically 100% accuracy. And if you use this particular quantum circuit, you can transfer the state from Alice to Bob with 100% accuracy in theory. But it does require Alice and Bob to communicate something. So, we'll talk about that. So, the scheme goes something like this. So, Alice has her unknown state, and actually she needs a second qubit for this one. So, she needs a second one just so that this thing works. Bob has the qubit which will eventually have this state. Okay. And initially, these 2 other qubits are set in the state 0. Okay, and then, there's a bunch of gates, Hadamard gate, C0, Hadamard. And then you do a measurement. And then these 2 measurements are made by Alice. And then what she does is she brings up Bob, tells the result of these measurements, and depending on that, Bob does some gates, and then at the end, Bob gets the state. Okay, so obviously totally not obvious by looking at the circuit why that is, but I'm just telling you what the circuit is, right? Okay. All right, so let's break that down. All right, so let's go through it sort of part by part. So actually you can think of this as being more or less in 3 parts. So the first part, which is the one in blue here, is that this makes like an entangled state between Alice and Bob. So this teleportation actually requires, sort of depends upon an entanglement. So another way to think of this, and sometimes people even write this, in the circuit, is that instead of saying I start with both states in 0, I could start with my state and then an entangled pair of qubits. That could be your initial state. Basically the same thing. Okay, and then the next part is, this is a measurement, and in a lecture or 2 ago, I was talking about how, if you have a measurement, and then I have some kind of U, I think I called it U basis or something. So if I do that, that combination is actually equivalent to measuring in some other basis. So, for example, a simpler example was something like this. If I did a Hadamard gate and did a measurement in the 0-1 basis, that's equivalent to actually measuring in the plus-minus basis. So if you could do that, or you could do that. It's basically the same thing. This is quite similar to that. If you have these 2 measurements and you have this control knot and a Hadamard, actually what it turns out later, as I'll show you, is it's actually equivalent to measuring in the entangled basis. Okay, so I'm calling it a measurement in the Bell basis because the Bell states are entangled states. And finally, this thing is called a classical correction because what happens is that Alice measures something, then Bob has to do something kind of conditional on those measurement outcomes. Okay, so we're going to break down each part bit by bit. So as I said, the first part is creating an entangled state. Okay, so let's just work through that. So at the beginning, we have this state, which is the state, and then the states 0 and 0. So that's our initial state. And then the first thing that we do is apply this Hadamard gate. Hadamard gate, apply that on T0. What I mean by T0 is this initial state. And so that's the previous state on the previous page. And if you remember, Hadamard gate on state 0 produces the state 0 plus 1. Right? So the initial state here after the Hadamard gate is like this, 0, 0 plus 1, 0. Next we're going to apply the controlled knot. And the controlled knot, if you remember, so this controlled knot is acting on the last 2 qubits. So this U here is applied on those 2 qubits there. And if you remember the controlled knot, the idea was that if the middle, well rather, the second qubit is 0, then you do nothing here. If it's 1, then you flip that one. Okay. So we apply that rule here to apply this operation on that part. So this is the control qubit, that's the second one, second qubit. So that's 0, so we don't have to do anything to that state. So that's that term there. For this one, we've got 1, so we've got to flip that one. We've got to flip the third qubit and that qubit. And so we get the state 1, 1 here. Okay, so actually we did something like this already couple of lectures ago. So after this blue block here, basically what happens is that we've got this state, and then we've got this 0, 0 plus 1, 1 state. That's this entangled state, which we've encountered before, also called a Bell state. So just pictorially, situation that we have at the moment after this blue block here is that Alice still has her original state, and we've got these 2 qubits that are in this entangled state. Okay, so the next step is we're going to do this block here. This is the measurement in the Bell basis. Okay, so this is just what I just explained before. So this combination just changes the basis of the measurement. And the basis for a single qubit, we've already seen, like, it could be like 0, 1 or plus minus. But for 2 qubits, actually, it's a bit sort of hard to imagine, but it's also possible to measure in a basis that is itself entangled. Right? So here, this 4 set of states actually forms a basis because all 4 of these ones are orthogonal to each other. So you can just sort of quickly test that out. So for example, if you had the state taking the inner product of two of these, say the first two of these states here, right, these ones. So if you work this out, so the factors of 1 over root 2 just give a half, and the inner product between 0, 0, this one is 1, that one is 0, this one is 0, and this one is minus 1, so it's equal to 0. If I took the inner product between some other states, for example, let's look at this one, 0, 1, 1, 0. So in this case, it's clearly 0 already because 0, 1 doesn't even appear here, right? And 1, 0 also doesn't appear here. So there's no common terms, so this is always equal to 0. So these four states form a basis, and it needs to be 4 states because 2 qubits have 4 possible states. So the kind of the regular basis, the computational basis would just be 0, 0, 0, 1, 1, 0, and 1, 1. So that's sort of like the usual basis, if you like. But that's not the only basis, just in the same way that a qubit, you can have your axes and they can rotate and they form any kind of set of orthogonal states form a valid basis. So for 2 qubits, that's a basis, but also that's an equally valid basis. And by a linear combination of those, you can easily, not easily, but just you can write any state, any 2 qubit state. Okay, so that's basically what that green block does, but maybe instead of you can think of it like that, or you can simply think of it just like, okay, let's just progress through the circuit, just applying these gates. So that's also equally valid. So here, what we've got, so somehow this looks very messy, but so we had our state after step 2. So T2 was our state psi, and that's our state. And then the first thing to do after getting to this point is to apply this control knot. So, well, maybe it's easier if I just do it on the board. So let me just walk you through it. So that's our state after the blue block, and what we're going to now do is to apply a control knot between 1 and 2, where the first qubit is the control. Okay, so after you apply the control knot, it becomes, so this is not equals to, it's a new state now. So when this first qubit is 0, control knot doesn't do anything, right? So we can just let's multiply this out here and here, but we know that if this is 0, it's not going to do anything. So we just leave that as it is. Now for the second term, which has a 1, for the second term, because this is a 1, it's going to flip the second qubit, right? So this is going to be flipped, and that's going to be flipped. So this is going to be 1, 0, and 0, 1. Okay. So that's the controlled knot after there. And so I think if you expand out what I just wrote here, so you get 0, 0, 0 and 0, 1, 1. So we get 0, 0, 0 and 0, 1, 1. And this is 1, 1, 0 and 1, 0, 1. So this is 1, 1, 0 and 1, 0, 1. So it's the same. And now we want to apply a Hadamard gate on the first qubit. So if you remember, what Hadamard gate actually does, is to turn 0 into plus and 1 into the minus there. Yeah. So let's do that operation, Hadamard on 1. So that's easy, we just follow that rule. So we've got that plus, same thing, and over here it's minus, and same thing. Okay, but actually it's kind of easier for the next step if I write actually this part of the first two qubits in the 0, 1 basis, because that's the basis that we're going to be measuring in. So let me rewrite this. So this is going to be alpha on 2, 0 plus 1. That became 2 because there's a root 2 inside the definition of the plus state. This one is 0, minus 1, 1, 0, plus 0, 1. Okay, and then and then I can expand all that stuff out here. So if I expand all that stuff out there, I will get that state there. Okay, so it's starting to look like a bit of a mess, but but actually there's quite a neat way of writing this. So because I'm going to be measuring in the just the regular 0, 1 basis, so I can collect all the terms. So over here, I can collect all the terms that start with 0, 0. Okay. So what you'll notice here is that if you look at the first two qubits, this first term starts with 0, 0, and there's another term here that starts with 0, 0. Okay. Over here, there's a term here that starts with 0, 1, and also over here. Here it's a 0, 1, 0, sorry, and 1, 0, and 1, 1 on the first two, 1, 1 on the first two. So actually, if we factorize it like this, we can actually see something interesting happen. So what you see actually, because each of the third qubits is two terms, so if we look at the term with the 0, 0, we actually see on the third qubit, it's a state alpha 0 plus beta 1, right? And that actually looks exactly like the state that that Alice had. But this is the third qubit, right? And the third qubit is the one that actually Bob has. So already you can sort of see, this is something interesting has happened here, because what used to be on Alice's side is now actually on Bob's side. Now if we look at the other terms, for this 0, 1 case, so this is not exactly Alice's original state. It's because this part here is Alice's original state. This is alpha 1 plus beta 0. So it's kind of similar to Alice's state, but kind of not quite, or more precisely, the 0 and 1's been swapped. over here, again, it's looking a bit similar to Alice's state, but not exactly. It's basically the same, except that this one has a minus sign. And over here, it's sort of like a combination of what happened here and here. It's like the 1 and 0 is swapped, and there's also a minus sign. Okay. So at this point, that's okay. Very just an interesting observation. But actually, what happens when we actually perform the measurement is that each of those 4 terms comes out with the same probability. Okay, so when you measure it, so this was the state that we were just talking about. Now, if you go and measure it, then basically, that term or this term or that term, this term, there's 4 terms. They kind of collapse, right? That's what happens in a quantum measurement, and the state now becomes one of these 4 cases, right? So after the measurement, so this is at sort of step 5, it randomly becomes one of these 4 states. And each of those have equal probability, so quarter probability each one of those 4 happen. So, this looks sort of tantalizingly close to teleportation, because it's sort of like, well, okay, if this case happens, then yeah, it's actually exactly what we want. Bob, the 3rd qubit, has the state, and everything is right. But actually, for the other 3 cases, it looks kind of similar, but the state is a little bit messed up, right? So basically, the last step is to just fix up this fact that the state is slightly messed up, right? For the 3 out of 4 cases. So, so we can fix up the state by basically removing this, extra sort of bit flip. So this one, we noticed it was like a bit flip because the 0 and 1 were interchanged. Here, like it has an extra minus sign, so I call that a phase flip. Right? So basically, what this classical correction is depending on whatever case you get, you apply an extra x, which is a bit flip, or a z gate, and that will fix up this, extra factor that we've sort of ended up with. So basically, the rules for the classical correction are basically that so let's see, where's so here's the table for the 4 rules that Bob needs to do to fix up state. So if Alice gets 0 and 0, then Bob doesn't need to do anything because he's already got the correct state. If Alice gets 0, 1, then Bob needs to apply an X gate, because the initial state before the correction is this. So to fix that up, you get, if you apply an X, then it'll flip the 0 and the 1. So you'll get the correct state. Here the state was that it's got an extra minus sign, and so that you can fix up by applying the Z gate. So that fixes up that one. And this one was just like a combination of both. It's like it's flipped and it has a minus sign. So if we apply a ZX, then this will also fix up the state. And in all 4 cases, we actually get the state that Alice originally had. So, so basically, it would go sort of something like this. They had these 2 states. Alice does the measurement. And then Alice phones up Bob and said, "Hi, I just got 10." And then Bob goes, "Okay, so I'll look at my table here. Okay, 10 means I've got to do a Z." So he goes, "Okay, so I'll just apply Z to my state and I'll have your state." Okay, so that's the quantum teleportation circuit. So what have we achieved? Well, as I started off, we've kind of managed to actually teleport, or send a state from Alice to Bob without either of them actually knowing what it was. So this, of course, works for any initial state. So this state alpha and beta, these parameters are arbitrary. So you can start with any state and it will still work. And the main things that were needed was that Alice and Bob's qubits were entangled. So that first step, we started with this entangled state. That's kind of one of the things that you need in order for this to work. And also, there was this classical communication, this telephone line, that you needed to do this final fixing up process of the state. And the key thing that shows you that you've basically done something which you kind of couldn't do just from a simpler scheme is that, well, okay, even though it required this communication, actually in principle the fidelity or the accuracy of this is actually perfect, right? So in all four cases you get exactly the right state, and as long as nobody makes a mistake somewhere or your gates don't have errors or anything like that, in principle this works with basically 100% fidelity, which means that Bob will get the correct state that Alice had basically every single time. And this is different to the previous kind of measurement kind of strategy that we were talking about, where if Alice kind of does her best and measures the quantum state, tells Bob, the best you can do is 66%. Right? So if you look at like papers that sort of demonstrate this teleportation experiment, often they'll be talking about this classical bound, and so they'll be talking about this 0.66 fidelity, and they'll show their experimental data, and then they'll say that, well, look at our data, it's above 66%, so we definitely know that we're doing something kind of that is at least beyond this kind of strategy of measuring and then sending. Okay, so just to kind of sort of think about the significance of this a little bit. So one thing that you might have noticed is that actually there was no real concept of sort of distance to this whole thing, right? So this pair of entangled qubits could have been separated by light years, so long that you manage to prepare this pair of qubits. So that means that actually, if you had this kind of entangled pair connection that was separated, huge distance, then basically then you could just about instantaneously teleport this state to the other side, because there's actually not really any concept of any signal kind of taking some time to travel between the two parties. So Alice and Bob, as soon as Alice does that measurement, Bob actually already has one of these four states. Right? So actually, this is sort of, seems kind of weird because, how can something sort of be transmitted and, if they're separated by a long distance, then obviously it could end up being faster than the speed of light. And the thing that gets around this superluminal kind of teleportation is that it's only this classical communication step at the end that prevents you from actually doing this superluminal sort of teleportation. Because Bob will randomly get those four states, and even though they look kind of more or less like something like the states that Al started with, they're actually sort of four states which are so if you had a block sphere and say this was, so here's my x and y z axis, maybe I'll draw this in different color. So the original state was over here. Then you have basically four states which are equally kind of distributed along the sphere. So if we just go and plot these four states. So so we'll have one state which is so this was our state alpha 0 plus beta 1. Then we have another state which has a minus sign here, and that basically means it's like 180 degrees on the other side. So if we draw this triangle here, then there's another state here which is 180 degrees sort of on the other side. And if we do a flip on the so if we have this state, well, maybe it's better to write this as beta 0 plus alpha 1. Then this corresponds to the state which has been kind of rotated around the x-axis by 180 degrees. So I think for this state, it's going to turn out to be going down this way, and there'll be another state which, okay, a bit hard to draw, but there should be four states which are kind of at opposite ends in terms of the x and sort of z axis. Right? So it's basically like four states which have been rotated around the x-axis or the z-axis. And these four states always sort of give an equal distribution in terms of probabilities. So what this means is that when you do your teleportation, the four cases that you end up with at Bob will never really give any information about what Alice's original state was. So it's a little bit like the superluminal communication that we talked about several lectures ago. There's kind of no information that is actually effectively sent by at the end of the protocol before you do the classical communication. But once you've done the classical communication, basically it fixes up those four errors, and you have exactly Alice's step. Okay. Yep. Okay. Any questions? No. Okay. All right. If there's no questions, then we'll move on to the next algorithm. Okay. All right. Okay. So we'll be. All right. So next one is Grover's algorithm. So, okay, the picture I've drawn here, you might be like, what the hell is this picture? So it's a needle in a haystack. So if you're familiar with the English expression, finding a needle in a haystack, then essentially it's something to sort of imply that you have to find some small and difficult to find thing within a much bigger kind of range of things, right? So it's kind of to imply that it's very difficult to find. So you say it's like finding a needle in a haystack. And Grover's algorithm is exactly an algorithm that does this kind of task. So so Grover's algorithm was invented by, of course, Mr. Grover here, and actually this is considered probably one of the two very famous algorithms in quantum computing. So it's sort of like at the top of all the quantum algorithms everybody has in mind. There's Shor's algorithm, which was kind of the first algorithm that people were showed that you could do a useful task with an exponential quantum speedup. And a couple of years later, I think Shor's algorithm was 1994, I think. So a couple of years later, Grover came up with this algorithm, which showed also that quantum computers can do this search task much faster than classical algorithms. And so the reason why Shor and Grover are kind of the most famous, it's basically because these are actually potentially useful algorithms. So Deutsch's algorithm was okay, great. Okay, so it showed us that there's some kind of quantum speedup, but basically it was a completely useless problem, right? So you could easily dismiss it and go, okay, very nice theory, but has no real world applications. But the reason why Shor's algorithm and also Grover's algorithm, this really kind of kick-started this field of quantum information and really made it into a big deal, was really probably thanks to these two algorithms, because all of a sudden it turned into something which potentially could be something that's actually kind of useful, actually solve sort of real world problems, and has an actual impact on the world. And so there's nothing like captures something that captures the attention of people, that things that actually affect things in the real world, affect you. Yeah. So another reason why actually Grover's algorithm is interesting is because it actually shows it's actually provably faster than classical algorithms, which basically means it's a kind of algorithm that you know that it has to be actually faster than classical computing because it's kind of possible to prove that there's a particular limit on classical computers. Right? I think this was also the case of Deutsch's algorithm, but actually this is not true for Shor's algorithm, where there's an exponential speed up, but it's only an exponential speed up over the best known algorithm. So there's a possibility that you can actually factor numbers maybe even faster than what's available today. Maybe it just hasn't been kind of discovered yet. But in the case of Grover's algorithm, you can actually show, kind of prove, or it's more or less obvious that actually there's actually no algorithms that could possibly be done any faster than the kind of classical algorithm that basically I'll show you. Okay, so this is the aim. So we're going to basically talk about what this quantum algorithm does. So suppose we have the task that we would like to search some large database, and it contains like n entries. And the entries are sorted, well, usually databases, the entries are sorted, say, in alphabetical order, right? So, for example, here's just some random thing that I found. Contains, names, addresses, cities, and say license numbers. So this is obviously sorted by name, so it's in alphabetical order. So if a database is sorted by name, it's of course very easy to find a particular entry in the database. So you have a particular order, and you can quickly find whatever entry you're looking for because it's already ordered. But if it's not ordered, then it's a little bit more difficult to find particular entries. So if I were to say, where is license number, S5 7556921, then you'd have to sort of go through each one and go, yes, no, like this, and then you go, aha, yeah, there it is, there. So that kind of took, one strategy is just to start at the top and work your way down. So that basically took 11 kind of readings of this table, and then finally I found it, right? So in this case I was a little bit unlucky. It was more towards the bottom than at the top, but of course I could be completely unlucky if it was this one, or if I was very lucky, it might have been the first entry. But on average it will take, there are n entries, probably n over 2, right? So at least it's proportional to the number of entries. And essentially there's no other way of doing this problem, because if you know it's unsorted, the first time you look at it, what strategy can you possibly think of, right? It's kind of completely random, and so all you can possibly do is to go through each one, and probably the only thing that you can do is to kind of mess up and then start like reading the same number over like more than once. So as long as you don't read each element like more than once, then that has to be the most efficient algorithm to do this, right? So in kind of complexity theory, you would say that the complexity of such an algorithm is O(n), which have you seen this notation before? Anyway, it's computer science kind of stuff. So it basically
complexity.
Yeah. It's sort of like how if you say each unit step is to read an entry of this, right? And basically you want to find a kind of a proportionality law to know how long it's gonna take. So whatever your clock speed of your computer is and so forth, there's you might have to multiply that by that to get the real time, but then fundamentally the proportionality of how many steps this algorithm has to take is always proportional to kind of n. So basically you say that as the complexity of this algorithm is O n. Okay, so let's kind of more mathematically kind of frame this problem. Okay? So we've already encountered the oracle. That was we actually had something like that already in Deutsch's algorithm. So actually we can reuse a little bit of that stuff there. But in this case, the oracle is going to be something that basically tells us whether it's the element that we're looking for or it's not. Right? So this function f of x has some number of inputs. The inputs of this are basically the database indices. So we've labeled this database with some index. Okay, so here I've started from 1, but normally you start from 0. And this f of x is just something that says, yes, that's the thing that we're looking for, or no, that's not the thing that we're looking for. So it's either no, mostly no's, and then a couple of yeses, here and here. So those are the things that we're actually looking for. And, okay, so assume we've got something that tells us that. So in the case of my example there, it would be basically something like, for example, this was the one that I was looking for, S7556921. So it would be something, the function in that case would be, something like, subtract that from that one. And then, if it's 0, then that's the one that we're looking for. Okay, so that's sort of the function, and we can think of it just as some black box, as the thing that we need to check to see whether the database entry is the thing, is our target element. So in this framework, the task is obviously then to find, or basically invert this function, right? So essentially what we want to do is to say, okay, well, find the inverse of this function with respect to 1, right? And then, okay, there might be multiple solutions, but that's basically the thing that we want, right? But the thing is that often it's not so, easy to do that, to just invert this function, because, well, firstly, as I was saying, it's kind of randomly distributed in this case, so there's completely no order to it. Or even if it was something a little bit more sort of a real mathematical function, so I've sort of abstractified this so that it's, could be applied in any situation. But even in some cases, often there are functions where it's kind of easy to go forwards, but it's kind of hard to go backwards. And so this is a classic example of this is factoring numbers. So it's easy to find the product of 181 and 199. Okay, you've got some way of doing that. But if I told you what are the factors of 336,019, okay, then it's not so easy to do because you sort of have to go and try lots of different numbers and then see which ones divide into that number, right? So So in many cases, just finding the inverse is not really a viable kind of step. Right? Okay, so we're going to use a kind of setup a lot like with Deutsch's algorithm, where because remember when we had that function in Deutsch's algorithm, we had to come up with some circuit like this in order for it to be invertible, right? Because if we just sort of applied x to f of x, then that would not be a reversible kind of operation, and quantum mechanics needs to be reversible. So the setup that we're going to have is a lot like with Deutsch's algorithm, but with more qubits. So here's our input value, and in this case I've drawn a few lines here because the input is in our case generally going to be kind of quite large, so there's going to be lots of different elements. So we're going to need a few qubits to encode this. So this is called a quantum register. So for example, for 3 qubits, we can encode sort of eight numbers essentially. So 0, 0, 0 to 1, 1, 1 will give 8 different states. If we need more states, then of course we just add more qubits. Right? 3 is just the example. So we can have 2 to the little n states to encode our kind of table with n elements here. So big N in this case. Big N in this case would be 12, which you could do with, 4 qubits. 4 goes up to 16. Some of them are unused, but that's okay. And for the second row here, this is basically where we encode our sort of f of x, right? And remember, f of x is just a binary output. So this f of this function has as an input potentially, this x could be quite large. So something that goes anywhere 0 to a large number. But the output is only 0 or 1. Okay. So the output of this only needs 1 qubit because of it's only 0 or 1. And we're going to encode it like this, so that whatever this y was, then we just add f of x to y modulo 2. So we went through a kind of a discussion with Deutsch's algorithm with this kind of oracle, where if we start this bottom qubit in this state of minus, then basically what's going to happen is that the state where f of x is 1 is going to pick up a minus space. Do you guys remember that? So if f of x, okay, maybe we need to go through the circuit again if you don't. Okay. Run out of time today, so we'll go through it next lecture. But in Deutsch's algorithm, there was basically exactly the same argument, where if we have this particular input here, then effectively what that ended up doing was to add a minus sign to the states where f of x was 1. Okay. So ultimately, basically, this is the form of the oracle that we're going to use. Okay, so but I think we'll leave it there because I think that's a good enough place to stop. Any questions? Okay.